So let's go for this middle box here. What do the following components do? Well, I've said that this protects the circuit because it's a fuse. You can tell it's a fuse because of the line going through it. The resistor won't have a line going through it, even though it looks like resistor. And then you've got this resistor here with that arrow. This arrow suggests that the arrow can move back and forth. So this will alter the resistance, therefore it's a variable resistor. We've got a resistor here with like an ice hockey stick through it. I always relate ice hockey to ice, which is something to do with temperature because the ice is cold, therefore it's a thermistor. So as the temperature decreases, the resistance is going to increase, or vice versa. As that temperature increases, then the resistance is going to decrease. It's got that sort of opposite effect there. The same thing with these arrows, light coming in on this resistor. I don't know why they've put a circle around it, okay, but they have. And I've said here, as the resistance increases, the resistance increases as the light intensity decreases, so you've got that opposite effect again. So this is a light-dependent resistor, an LDR. And then you've got the diode on the bottom, which only allows current in one direction. And we kind of talked about that there, okay, the fact that you won't get that, when you switch the battery around, you won't get that coming down there. It'll just look like that. Let's go over to this box. This is... if A1 reads 4 amps, give the values for this one and this one. Well, going right back here, when we've got this little table, if you're still getting stuck, then we know that current is going to be the same in a series circuit. So let's go back over. So I know that it's going to be 4 amps everywhere. It's going to be 4 amps everywhere. You can imagine these 4 amps, as students walking around the table, and wherever you measure these, you're going to get 4 students, aren't you? You know, it's never, they can't split. There's no branches for them to split. Whereas in this one, if A1 reads 12 amps, so you've got 12 students coming around here, what's it going to be at A2? Well, it's likely that, and I've talked about if there was a fire, you're going to use 2 doors instead of 1. So these students now, they're going to be like, well, you go this way and I'll go this way. So it's likely, depending on the resistance of these amps, and this is why we can only estimate this, it's likely that it's going to be 6 amps here and 6 amps here. And then they'll all meet back and it'll be 12 amps again, because current splits. And in my mind, it might not be the best definition or way to think about it, but I always think of them as these little students walking around the desk. And if you got 12 here, then the easiest way for them to get around is to send 6 this way and 6 this way, and then back up, and we all meet together at the end, and everyone's happy. Let's do this bottom one, and then I'll sort of move up then. What do the following components do? Comment on how they are used. So your voltmeter measures the voltage, must be placed in parallel over a component. So just look at this circuit here. I know we haven't come to this, but if I'm going to stick a voltmeter over that, I'm going to stick the voltmeter over it. Okay, and stick a V in there. I'm not going to stick it in series. So let me just undo all that. And then the ammeter, and you can see there, can be placed in series, and it measures current. Okay, never do you want to see an ammeter coming across a bulb. So let's do this one. What is the equation for Ohm's law? Well, Ohm's law is connected with this fixed resistor at a constant temperature, and it's also connected with this standard test circuit. Okay, because what you're doing from this standard test circuit is you're measuring results, which will produce a graph like this, and from this, because it's all directly proportional, like I said, if it doubles here, it's going to double there. If it triples here, it's going to triple there. We can use a nice little equation called Ohm's law, which is I equals V over R, or V equals I times R, or it could be R equals V over I. If you use this triangle, you put your finger over whichever one you're looking for to calculate what you need. So it says there, calculate the current. So we're looking for current, so I don't know my current. This is the way I suggest doing it, writing out what you've got, and then you need to be writing the formula down to pick up marks. And substituting these letters for values, and then you need, obviously, units at the end. So it says there, current is, don't know, voltage is 12, my resistance is 4 ohms. Let's bang it into an equation or a formula. So if I'm looking for I'm looking for current, sorry, I'm going to cover I, and I can see my V is on top of R. So it's going to be V over R, so it's going to be 12 over 4. And that's going to give me 3 amps. Let's do the bottom box, and then I've got one more box to do. Explain what happens to the resistance and current when resistors are connected in series. Well, if they're in series, they're going to increase, and I'm going to demonstrate that now. So it says calculate the total resistance of 3 6 ohms bulbs in series. So if they're in series, it means one after the other. So I've got 6, 6, 6. And the formula is total resistance, RT, is going to give me R1 plus R2 plus R3. So that's just 6 plus 6 plus 6. And it's 18 ohms, which is way more than so if you've got 6 ohms and you haven't got anything else, and you add another 6 ohms, it's going to increase. And you add another 6 ohms, it's going to increase again, that resistance. Whereas back up in the parallel circuit, if you keep adding resistors, and you can try this yourself, you can always add another 6 in there and stick. So you can stick 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6, and you will see these values start to decrease. It will actually go down. This number will actually go down. It'll be less than 2 ohms, and that's why it's really good to use in you know, everything you see wired up, apart from Christmas lights, and even nowadays, even Christmas lights are starting to use the parallel system. It's going to be used because it's so efficient. And then this last one then, if the power of a light is 60 watts and the current flowing through it is 3 amps, what is the voltage supply? So we're dealing with power now because we've got watts. So again, let's write down what we got. So my power is 60 watts. My current is 3 amps. What's my voltage? I don't know. I'm going to look in the front of my exam book, and I'm going to identify that formula, which is I think it's PIV is found in the front of your formula. But again, we're going to show you down your way. So there it is, PIV, or PVI in your formula book. It's the same. So PVI is the same as PIV because these are times each other. These are tied up together. You can do those either way. When I was in school, I remembered PIV, so PIV, but they're given to you, so you just may as well use them. And when you've got anything tied up, we'll come back to this now. So I'm going to use my formula triangle, PIV. I'm looking for V. So V I cover up is P over I. So it's going to be 60 over 3, which gives me 20 volts. What is the resistance of the bulb? Well, I'm going to use now the one that's found in the front of your book is P equals I squared over R. I can't really get down. Sorry, that was just me. Can't get down there. P equals I squared over times R. Sorry, not over R. So these two are tied up, so I'm going to push this P up, and it's going to give me a triangle that looks like this. So in this case, I need to know the resistance. I'm going to cover R. It's going to be P over I squared. P over I squared equals 60 over 3 squared. Well, 3 squared is 9, so 60 over 9 is going to give me 6.6 ohms. And then just to show you what I was doing there, draw formula triangles for each of these. Big debate here. Do we teach you how to rearrange, or do we just show you how to do the formula triangles? Spoke to Wooly a lot about this. He suggests learning how to do this, but then I think it's just as easy to just, if you know that they're tied up, if you know V is connected to I, you just got to push this P up. And you don't really have to think about anything else then. You're just covering up what you want. So you just push in, if they're connected, you push this letter up. If they're not connected, and you've already got V on top of something, then V just stays on top. And this fella comes down. And I mean, I think that's really easy. This E is going to go up. Okay, this P is going to go up. And I think for the formulas that we use in physics, that's probably the best. That's my gut telling me that's the best thing to do. I mean, there are other ways you can do it. You know, if and I'll demonstrate now. If you've got P equals VI, and you know P to be, I don't know, let's just say 60, and we don't know V, but we know I is, let's pick an easy number, 3. Okay, what you would do then is because V is tied up with 3, you would divide both sides by 3 to get rid of this. So that would become 60 over 3 equals V, and so on. But like I said, you know, you can either do it that way if you're good at maths, or it just might be easier to use those triangles. Anyway, I'm going to leave it there for today.